Hello, my name is Derek Montañez, and my project is on machine learning model analysis for machine failure prediction. In my presentation today, I'll be going over the roadmap, which is specifically the objective, data set, and preprocessing methodology, results, looking at performance and key insights, and as well as the conclusion. So objective here is to compare performance and architecture between different machine learning models with an emphasis on ensemble classifiers for the machine predictive maintenance classification dataset provided by Kaggle. And my simple classifiers include KNN and decision trees, and my ensemble classifiers include random forest, AdaBoost, and XGBoost. So why is this such an important problem? Machine failure is one of the biggest hindrances for project managers and construction managers in terms of project deadlines and project budgets. And it's one thing that I know a lot of project managers and construction managers would like to keep track of, providing analysis and prediction for machine failure. So I divided this into three sections. First is the money aspect. So according to Sensei, a corporation out of Austin, large facilities lose 27 hours a month to machine failures on average at the cost of around 530,000 an hour for unplanned downtime, which is a very substantial amount. And according to Bin95, another company, there are 60 different costs that can accumulate from machine failure alone. So it's not just costs to repair the machine, but these costs can be spread out throughout the project and as well as into the company. And also looking at is injury. Workplace injury chances skyrocket due to machine failure, and these injuries can range from very small and in some rare cases can lead to fatality. And the last final thing I want to point out is the data available. So currently there is no stop of industrial production anytime soon, and this means that data from sensors are generated at exponential rates, and this data can be used very efficiently and effectively for this specific task. So our dataset contains 10,000 samples of synthetically produced data for machine maintenance classification. And the authors of this dataset from Kaggle noted that this was synthetically made because true predictive maintenance classification data is very hard to obtain. So they did the best of their knowledge reviewing previous and documented prediction maintenance failures and being able to create synthetically generated new data based off that. And some of the features that are contained in this dataset are process temperature and air temperature, which are measured in Kelvin, rotational speed, torque, tool wear. And I have a multi-class problem with the class containing no failure, heat dissipation failure, power failure, overstrain failure, tool wear failure, and random failures. And as we can see from the support for each class, there's an extreme imbalance with the no failure class having around 9.6 thousand of the total 10,000 samples, and the rest of the roughly 400 instances being spread out through the rest of the 5 classes. So some of the pre-processing steps that I took. So like I said earlier, this data is synthetically made, so there is no missing data initially from the raw data from Kaggle. But I did need to do some feature selection. I removed the ID and product ID columns from each instance, as these are just identifiers and don't really help in help give any information for our models and architecture, and just introduce noise. I then had to do label encoding for type attribute, specifically one hot encoding. And the type attribute is basically an assessment on the quality type of the machine. So there's low quality, high quality, and medium quality. And the variables that were kept were the type, which I one hot encoded, air temperature, process temperature, rotational speed, torque, and tool wear. And again, my output variable is failure type. And one thing I wanted to note is there was another column of the dataset called target, which was a binary classification output of either if the machine failed or not, but I wanted to use the failure type output, which indicates whether a failure happened or not, but also indicates which type of specific failure happened, because I feel this is more useful um, and provides more insights to project managers and construction managers. So some EDA and insights. This is a pair plot showing the feature correlation between different features. As we can see, process temperature and air temperature have a very positive correlation, whereas torque and rotational speed seem to have a negative correlation with each other. And all the other feature combinations seem to have no true correlation. Some more EA insights. I want to see the mean temperature of air temperature, the mean values of air temperature and mean values of rotational speed and how they spread out across different classes. As we can see here, air temperature has the highest mean value for heat dissipation failure, which is not a big surprise, and rotational speed has the highest mean failure for the power failure class as well as the two-wear failure class. So model selection and class imbalance. The way I handled model selection was using randomized search CV, which tests different hyperparameter values for generating the best model. And the scoring metric that was used to generate or decipher which one's the best was the F1 weighted score. Since this score takes into specifically class imbalance, whereas other metrics won't be as good, such as accuracy, which doesn't take into account class imbalance and can be misleading. And the class weights, I apply class weights to the different classes, penalizing the majority classes and improving or giving higher weight to the minority classes. So going into our model architectures for KNN, we were able to achieve, or from random search, we were able to get a KNN model that had 9 nearest neighbors with the Manhattan distance, and the distance metric was, and distance was used in the weights. And we were able to achieve a macro average score, F1 score of 27.17, which was the worst performing model out of all of them. As we can see here, the majority class performed really well with no failure getting a 98.39 F1 score. And one interesting thing to note is heat dissipation, random failure, and two-wear failure all failed to be predicted at all. This is due to the major class imbalance. And we can see that overstrain failure and power failure had high precision scores but lower recall scores, meaning that both of these classes, this model was very selective with these classes, but when they were selected to be true, they performed very well, minimizing the number of false positives. And next, architecture decision tree. This is the architecture of the decision tree that was returned from random search. And we can see that the model was able to perform a macro average F1 score of 59.02. And to go back to why I'm using macro average F1 score um, to categorize or label these architectures is that accuracy is a bad metric to use, especially for imbalanced data sets. And this macro average F1 score takes into account class imbalance. So looking more at the confusion matrix, we can see that no failure performed relatively well, and we can see that heat dissipation performed really well with the F1 score of 92.92. And we can see that the precision and recall are relatively high as well, meaning that it was able to predict a good amount of the true heat dissipation class and as well as having a very low false positive rate. And we can see that the overstrain class performed averagely, and the power strain class, similar to what we've seen, has a very high precision and a lower recall score. And again, we get very poor results for random and two-wear failure. Going to some insights on decision trees, we can see that these are the feature importances that were computed from decision tree model, and we can see that tool-wear and torque were deemed to be the most important features, whereas type M, type L, and type H features were deemed very not important at all. And the way that feature importance was computed is to take the normalized total reduction of the criterion brought by that specific feature, basically the importance of each feature. Going on to our next architecture, starting with the ensemble architectures, is random forest. These were the hyperparameters that were introduced with random search CV, and we're able to generate a macro average F1 score of 52.32. And we can see here, similar to all other classes, the no failure class performed really well with the F1 score of 98.97, again due to it being the majority class, as well as heat dissipation failure performed relatively well. And one thing to note here that we haven't seen before is a lower precision and a higher recall, meaning that most of the heat dissipation true instances were labeled, but again, a higher false positive rate comes from that. And we can see that for the overstrain and power failure class, you see the same pattern that we've seen in other models with a high precision and low recall. And again, same story with the random and tool-aware failure classes, is that they're unable to predict these classes at all. And looking into the insights, we can see that again, it follows the same distribution as decision trees, is that random forest gave the highest importance to both tool wear and torque, whereas the different types were the lowest importance. And one thing I wanted to note here is that I initially believed that process temperature and air temperature were initially going to be higher importance features due to how well the heat dissipation class has been performing across architectures. And the next model is AdaBoost, and these were the features, hyperparameters that returned from random search CV. And we were able to achieve a macro average F1 score of 53.97. And looking closer at the classes, again, similar story. The no failure class performed relatively well with a 0.99 F1 score. And we can see that the model performed really well for heat dissipation, getting F1 score of 0.89 and that value consistent for precision and recall. And again, the same story that we've seen with the overstrain and power classes, having a high precision and low recall score. And again, with the random failure and tool wear failure being not being able to be predicted at all. And looking at the feature importance for the AdaBoost model, this was the most interesting feature importance insight, in my opinion. The reason being is just the difference between the first highest importance class and the second. We can see that toolware has around a 0.8 importance, whereas the second highest torque is around 0.08, so a 10 times increase, which is something that we haven't really seen in any other architecture thus far, but follows a similar format of feature importance across the features. So our last architecture looked at was XGBoost, and these were the hyperparameters returned from random search CV, and this model performed the best. It generated a macro average F1 score of 59.76. It performed really well on no failure class, as well as performing well on heat dissipation class. And one interesting thing to note here is that it gained a higher recall than precision, meaning that it was able to um, recognize a lot of the true heat dissipation points, but also not having that drastic of a value for false positives. And we can see here that the overstrain and power class follow the um, same kind of pattern with a low precision or lower precision and a high recall. You can see that overstrain was able to predict all true overstrain values, but again, that comes with having a lower false positive rate. And again, to similar architectures, we see that random failure and tool-aware failure were not being able to be predicted at all. So these are the XGBoost insights. And the thing that stands out to me the most is that the type M has a high feature importance, which is something that we haven't seen in previous architectures at all. And for this feature, for this model, torque and tool wear also have the two highest feature importances. And again, one thing that I wanted to reiterate is that I initially believe process temperature and air temperature we're going to have higher feature importances due to how well the heat dissipation class has been performing across all classes, but that didn't seem to be the case. And finally, a comparative result across all architectures in terms of macro average F1 score. And again, just to reiterate, accuracy was a bad comparison metric for imbalanced data sets, specifically for ours, in the case that a model predicts every instance to be no failure, that would generate around a 96 or 97% accuracy. But that's not a true indicator of how well the model is performing. So I wanted to use the macro average F1 score, which takes into account class imbalance. And we can see that XGBoost performs the best. And the last note that I wanted to put here is we can see that there's a little trade-off between simple architectures and complex architectures. Initially, I thought that decision trees was going to be one of the worst performing architectures, but we can see that it outperforms random forest and AdaBoost, which I thought was pretty interesting since random forest builds decision trees or tests multiple decision trees. So I thought this was a pretty interesting result, and I could hypothesize that random forest may have overfitted the data slightly. So my conclusion is that this project provides insights into the task of machine predictive maintenance using analysis from machine learning models. Specifically, I looked at simple classifiers and ensemble classifiers. And XGBoost was deemed to be the best algorithm suited for this data with a macro average score of 59.76. And feature importance between models were slightly consistent, with torque and tool wear consisting of the feature with the highest importance across all architectures. And lastly, I would like to train the XGBoost model using actual company-specific data, as I feel this would give a lot more personable insights for each specific company, given the amount of data they have for their specific machines. And that is all. Thank you very much.